Hi there, folks. Today we're looking at surface areas and volumes of similar solids, okay? And just like any other similar figures that we've had, similar solids are solids with the same shape and all the corresponding dimensions are proportional, all right? And, when we look at the similar figures, we looked at side ratios to make sure that all the sides had the same ratio, to make sure the sides were proportional, all the angles were congruent. Similar solids are kind of the same thing. It's just a three-dimensional representation of that same concept, okay? And so if similar figures worked one way, similar solids are going to work that same way. We're just talking about a figure that's in 3 dimensions now. Okay, so here we want to identify if the solids are similar. So once again, we're going to identify the shape of this thing. And when we talk about shape, we mean the same types of polygons. Those polygons would have the same angles. So if one set has regular polygons, the other one should have regular polygons for the bases, that kind of thing. That's what we mean by the same shape. So identify if the solids are similar. So if we look at these first two, the first one is a pentagonal prism. And the second one is a triangular prism. So right away, these are not even the same shape. All right. So I don't want to bother comparing the sides here. They're not the same shape at all, so they can't be similar. All right. And so comparing the sides, I might find out that there's some proportionality between the measurements that are given, but that doesn't matter if they're not even the same shape. These can't be similar solids if the shapes are different. Okay. So these are not similar solids. And I would just say prisms for this one. Okay, so these are not similar prisms because they're not the same shape at all. So there's no use in even comparing the sides to check for proportionality. If I look at these guys are at least the same shape. When I look at this, they're both rectangular prisms. So the first one's a rectangular prism. The second one is also a rectangular prism. And so now I can start to look at this and say, well, they're the same shape, the same basic shape. Let's talk about the sides now and check for proportionality. And so I just look at the ratio of the sides. So like here, I compare the 10 and the 5 and say, okay, the ratio of those sides is 10 to 5, which of course I can reduce to a 2 to 1. Okay, so that first set of sides, the ratio is 2 to 1. I could look at like these sides down here and say, hey, the ratio 14 to 7, well, that's 2 to 1 when I go from the the larger polyhedron to the smaller. And then the last set of sides, I've got one more set here, the 5 and the 2. If I reduce that, well, it doesn't reduce, it's 5 to 2. And so as I look at these ratios, the first two sides I compared were proportional because they had the same ratio, but that third one doesn't quite fit the mold. And so because I don't have proportionality with all of these sides, I don't have similar solids this time. Okay, so these are not going to be similar. Okay, and I could be more specific. I'd say they're not similar rectangular prisms, or I could be more generic. They're not similar polyhedrons, or just say they're not similar solids here. Okay, but they're not similar because there's no proportionality there. If I look at these, once again, I have two rectangular prisms. So the shapes, the general shape is the same. So now I can talk about comparing the sides. So I have this similar shapes. What I need now is to see if the sides are proportional. And so I start comparing these. So once again, I look at a set of sides like the 6 and the 9. And I say the ratio here is 6 to 9, which reduces to 2 to 3. And then I compare the next set of sides, maybe the 4 and the 6. And once again, it's 4 to 6, which is 2 to 3. And then the last set of sides here, the 2 and the 3, when I compare those, it's 2 to 3. And so no matter which sides I compared, I got the same ratio, which means the sides are proportional. The sides of the smaller solid are proportional to the sides in the larger solid. So I have the same shape. I have proportionality when it comes to the sides. So these are similar solids. Okay? So I'm going to say these are similar prisms. Okay? And that's it. We look for the same shape. We compare those shapes to see if they're proportional. If those two things happen, same shape with proportionality, then I have similar figures. If I look at these guys, I've got cylinders this time. And cylinders are just a little bit different because instead of comparing the sides, we're going to compare the radius and the side, or the diameter and the side. So we need to compare the circles in some way. And circles are automatically similar if they're, all circles are similar to one another, but we check the proportionality of that similarity based on the radius or the diameter, okay? And then the other piece of the cylinder here is that I have the height, so I would compare those as well. So it's a little bit different. Instead of just comparing sides, I'm comparing sides, but I'm also comparing like diameter and radius and that kind of stuff. Okay, so when I look at this one, once again, they're a similar type of shape. They're both cylinders, so I'm on the right track there. So I have the same shape style. Now I just need to check for proportionality. And so once again, I compare these things. And so like here, if I compare the sides, I'll start with those. I've got 10 to 5, which is 2 to 1. And now I have to compare these guys. And when you look here, I've got a 4 and a 4. And please don't make the mistake of saying, oh, 4 to 4, that's 1 to 1, so these are not similar. Those are not the same measurement. One of them is a radius and the other one is a diameter. And so what I have to do here is I have to think of these in terms of the same thing. So if I want to look at this guy as the diameter, I better look at this guy as the diameter, which is 8 meters, okay? And so what I'm comparing there now is I'm comparing the 8 to the 4, so 8 to 4, which is 2 to 1. Okay. Likewise, I could compare these in terms of the radius instead. Maybe I want to look at this and say, you know what? I want to compare this as a radius. So I have to think about the radius of this guy, which is 2 meters. Okay. And now I can say, oh, 4 to 2, which is 2 to 1. All right. So make sure you're comparing the same thing. Don't compare a diameter to a radius. Compare a radius to a radius. And so as I look at this thing, I have the same shape. The important pieces here, the radii, the diameters were proportional with the side lengths. So these are similar cylinders. Okay. I've got the same shape and I've got proportionality. Taking a look at something like the scale factor and how that relates to surface area and volume, one of these pieces we kind of already know. If you think back to when we looked at similar figures in terms of perimeter and area, we decided, or we discovered, that when you look at the ratio of the sides, it's the same ratio that we experience when we look at the perimeter. Okay, and then when you look at the ratio of the sides versus the ratio of the areas, the ratio of the areas was the squared version of the ratio of the sides. So when we take that scale factor for the sides, well, if we square it, that gives us the ratio for the areas. And it's the same thing here. So that area thing that we already discovered with similar figures, that's true here for surface area as well. So when we're talking about similar solids, that still holds. And again, when you think about it, it makes sense in terms of the units. All right. When you think about perimeter, it's just a regular unit, so unit to the first power, and it has the same ratio as comparing the lengths of the sides. Okay. But the area, now we're talking about squared units, and the ratio is the same ratio as the sides, but squared. Okay. And now volume, taking this a step further, volume is cubed units, so it's the same ratio as the sides, but cubed this time. And so if we kind of think about that relationship, when we compare the sides, it's A over B. When we compare the areas, it's A squared over B squared. Then we compare the volumes now, it's going to be A cubed over B cubed. Okay? For example, it says two similar solids have a scale factor, so that's the ratio of the sides of 2 to 5. The surface area and volume of the smaller solid is 36 and 512 respectively. Find the surface area and volume of the larger figure, okay? And so the first thing we want to do, let's talk about the scale factors. Let's talk about the ratios for each of these things. So what's given here is the ratio of the sides. So when I look at just the side lengths, the ratio here is 2 to 5 when I compare the smaller figure to the larger figure, all right? If I do the same thing then for area, the ratio for the area is going to be 4 to 25. It's the same ratio, but squared. That's the relationship that this has. So the ratio for the areas, when I look at small to large, should be 4 to 25. And now the volume of this thing, and this is the thing that's new here, well, it's going to be the same ratio, the 2 over 5, but the cubed version of that ratio, so 8 over 125. okay? Those are my ratios for the different things. When I compare the sides, the ratio is 2 to 5. Areas is that squared, 4 to 25, and volume is that thing cubed, okay? And so to find these missing values, I can do this literally setting up proportions. I could say, well, what I have here is when I compare these, let's look at the areas first. So here I have the area of the smaller shape is 36. So let's set up a proportion for area. I know that the ratio for the area should be 4 to 25. And again, that's the small figure to the big figure. Well, over here, let's compare that. It should be proportional to the actual areas. Well, the area of the small figure is 36, or the surface area. So now I can find the area of the larger figure. I don't know what it is yet, so I'll call it x. But now this becomes literally a job for my calculator. I cross multiply the 36 times the 25 gives me a 900. And now I divide each side by that 4. So I find out that x equals, or the surface area of the larger figure equals 225 square meters. And again, it's because I already knew how these are supposed to be proportional. I already knew what the ratio is. So I set up a proportion. The ratio is supposed to be 4 out of 25. So let's look. The ratio is 36 out of what? All right. And now I can do the same thing with the volume. Again, the volume, the ratio should be 8 to 125. And that should equal the actual ratio I get when I compare the volumes. And so if I compare the volumes, the smaller figure has a volume of 512. The larger figure, I frankly don't know what the volume is, so I'll call it y this time. Okay? And once again, this is basically a job for my calculator. I cross multiply, and that gives me a 64,000. And then you divide each side by that 8, and you get an 8,000. And again, that's cubic meters. Okay? So again, it's just using the ratio that we know it's supposed to be and setting up a proportion. Okay? That's one option. Option 2, and this is probably the option that I use more often, is I just think of that ratio as a scale factor, as a thing that I multiply by. And I say if I want to go to the thing that's tricky about this is which version of the ratio do you use? Like I set all these ratios up as the small versus big. I could have set each one up as big versus small, 2 over 5, or 25 to 4, or 125 to 8, okay? And so keep that in mind. You know, it's kind of up to us. We kind of decide, unless the problem specifies, how we write that ratio. We could just find the new value by multiplying, but we have to multiply by the right ratio. For example, for this one, I'm going to start with the 36 and say, okay, I want to get to the larger one, so I'm going to multiply by the scale factor for the area, which is 25 over 4. Okay? And that's the scale factor that I have to use. And when I do that, it gives me the 225. Again, that's square meters. Okay? And keep in mind, if I multiply by the wrong one, if I multiply by 4 over 25, it's going to give me a smaller value. And just think, does that make sense? All right? Yeah, you're going to multiply by this ratio, by this scale factor, but I'm going from the smaller value to the bigger value. Make sure the value gets bigger. And if it doesn't, yeah, you did the ratio wrong. You got to flip it. Okay. Likewise, I can do the same thing with the volume. I start with a 512. Again, to make this value increase, I got to multiply by this ratio, the 125 over 8. Okay. And when I do that, it gives me the 8,000 cubic meters. Okay. So I can think of this thing as a ratio instead of proportions. I can think of it in terms of proportionality, or I can think of this as a scale factor. You just got to be careful about which version of the ratio you use when you multiply and use the scale factor to get the missing value. Okay. If I look at this one, it says two similar cubes have volumes of 229 and 1,331. Find the scale factor of the cubes. And again, the scale factor is basically the ratio that we get when we compare the sides. And so as I look at this thing, what I have here, if I kind of break it down this way and think about it and say, okay, well, the sides, remember, generically have a ratio of A over B. The area is A squared over B squared. And the volume, well, is A cubed over B cubed, okay? And so when you think about that, the scale factor that I have is the volume, okay? And the ratio for the volumes is the 729 over the 1,331, okay? And so basically, I'm just saying, hey, the scale factor for the volume is a cubed over b cubed, and that happens to be 729 over 1,331. If I want to go back to the original scale factor, well, it's just a matter of taking the cube root of each of these things, okay? If this scale factor represents a cubed and b cubed, well, I take the cube root in order to get back to the originals, okay? So again, a job for my calculator, the cube root of 729 is going to give me a 9. And the cube root, again, I'm just using my calculator for this, it's going to give me 11. Okay, so I just take the cube root of each of these guys on my calculator, cube root of each of them, and I end up with a 9 and an 11. And so essentially that's my scale factor, okay? The ratio of the sides is going to be 9 to 11. And I could write it like this, 9 to 11 from the smaller one to the bigger one, okay? That's my scale factor, all right? I could write it like this, or I could leave it as a fraction. It doesn't matter. It's okay to leave it as a fraction, all right? But then I could also find the ratio for the areas as well by squaring those things, 81 over 121, okay? So there's a lot of different things that we can do once we have that original scale factor, okay? For this one, the lateral area of two similar cans are 1019 and 425. If the volume of the smaller can is 1157, find the volume of the larger can. And so once again, the thing that's tricky here is I can't go right from the area to the volume in terms of the scale factor, okay? I have to work my way back through the original scale factor. And so right now, this is the area. So the area is the 1019 compared to the 425. That's the ratio I get. And what I need is the volume. Well, I kind of have to go backwards to work forwards here. I need to work backwards to the scale factor for the sides. And so thinking about the scale factor for the sides, well, if I have the area is the squared version. To get back to the sides, I have to take the square root. So essentially going to be the square root of this guy over the square root of this guy. And I don't believe those are going to come out nicely, so I'm just going to literally leave them as square roots for right now, okay? It doesn't matter. And now when I go to volume, the volume is just that scale factor cubed. And watch what I'm going to do. There's no sense in bothering picking up my calculator right now. I'm going to cube that guy. And then here I'm going to cube this guy. Oh, sorry, 425. And so that's my ratio, that's my scale factor here, and I can use that to find the new volume, all right? I don't need to plug it in, I don't need to round it off, I can just leave it in terms of those square roots and cubes until I'm ready to plug it into the calculator. And so once again, there's two ways I can do this. I can set up a proportion, so I can say, hey, this ratio, the square root of 1019 cubed, over the square root of 425 cubed, that ratio should equal the ratio of the volumes. And it says the smaller can, which I have in the denominator this time. And I want to solve for the larger can, okay? And I can easily cross multiply and solve that. Again, the second option is just to do this in terms of multiplication. Say, hey, you know what? I'm going to take this guy, the 1157, and I'm going to multiply that by my scale factor. I need this thing to increase. So I'm going to do this version of the scale factor. And again, from here, it just becomes a job for my calculator, okay? Different teachers will maybe have you round this off to do the scale factor for the volume. But either way, it's going to work out just fine, okay? So let's see here. The square root of 1019, and then raise that to the third power, times the 1157, and then divided by, and I'm just punching this into my calculator. I like to punch it into my calculator in kind of chunks here. Makes me feel more comfortable. And when it's all said and done, I've got it punched in. Here, when I cross multiply and solve, I get the 4295.5, and that's cubic centimeters. And here, when I multiply this out, I get 4295.5 cubic centimeters. Okay? So again, I'm just using that scale factor and plugging away. For this one, the volume of a solid is 1836. What is the volume in cubic yards? And so this one was in cubic feet. And here's one of the things that this is really beneficial for. Think about the factor conversions that you use here. When you think about the conversion from feet and yards, the conversion that we have here is this. It's 1 yard goes with 3 feet, okay? But here, I don't want to go from yards to feet. I want to go from cubic yards to cubic feet, okay? And so the idea here is I have to think about this ratio in a little bit of a different way. Like if I wanted area, I could square each of these, and that would give me the new ratio. So it would be 1 to 9 square feet, okay? And now likewise, the ratio for the volume is going to be the same ratio, the 1 to 3, but cubed this time. So 1 cubic yard is going to go to 27 cubic feet, okay? That's how we kind of use this thing. We use that idea of, hey, the relationship here, the scale factor, if I want the relationship for the area, I square that same ratio. I square that same scale factor. If I want the relationship for the volume, I cube that same relationship, okay? And so we can use that to come up with different ways to convert these things. And so for this one, I just have to kind of do my factor label. I revert back to science class, and I say, okay, in science, I start with cubic feet. And now I need the cubic feet to cancel, and I want cubic yards. And so thanks to this ratio, I've come up with a ratio right here that I can use for cubic yards. 27 cubic feet is 1 cubic yard. And now what happens is these units cancel. I'm left with cubic yards, and I'm able to do that all in one simple step instead of having to cancel out feet 3 times and that kind of stuff, okay? And so once again, this is a job for my calculator, the 1836 divided by that 27. So I get 68 cubic yards, okay? But I essentially just took the scale factor, the ratio, the conversion between yards and feet, and I changed the relationship to volume, okay? I went from that linear relationship to that cubic relationship, okay?